Chapter 9, Section 1. In our study of calculus, we've learned about the practical application of functions in real-life scenarios. For instance, by saying that the amount of money you would pay for a speeding ticket T is a function of your speed past the speed limit L, we understand that there's a relationship between the speeding and the fine. But what if it also depended on the number of previous violations V? Now we have two variables that can affect the outcome of our function and your fine. In this section, we're going to learn how to incorporate a second variable into our function. Two variable functions. So let's say the weekly consumption, C, of beef in pounds of an average household is a function of the price, P, per pound of beef, and the annual household income, H, in thousands of dollars. So now again, how much you consume is based on how much the beef costs and how much money you make. To represent this, we can write it like this. C, the total cost, or the consumption, is a function of the cost and how much you make. P represents the price of the beef, and H represents your household income. Usually we just have f of x, but now it's a function of two variables. C here is the dependent variable. F is the function giving C a value based on what P and H equal. And P and H are variables that are going to vary, and they are going to be in the domain of our function. So here, it'll make sense that P is going to be a positive number, and that H is also going to be a positive number. If one variable stays constant, and the other variable is increasing or decreasing, then the function as a whole is said to be increasing or decreasing respectively. We'll learn how to calculate increasing and decreasing functions later in this section. Okay, so let's look at a table that might represent this consumption. So, when we have a table that depends on two variables, it's set up a little bit differently than when we just have one variable. So the beef consumption is a function of price and household income. So across the top, we're going to put the different prices of beef. So here we have $3, $3.50, $4, $4.50. Down the first column, we have the household income in thousands. So this would represent $20,000 annual income, $40,000 annual income, $60,000 annual income, so on and so forth. So our values for each variable, one goes across the top row, one goes down the first column, and then the consumption itself are the values in the middle. So what if we wanted to talk about the amount of beef consumed by a family who wants to buy at $3.50 a pound and has an annual income of $80,000? So $80,000 is represented right here by this 80, by this row, okay? And then $3.50 is represented by this column, so we look for where they intersect. So $80,000, this row, $3.50, this column, their intersection is 5.29. So that tells me that if we're going to buy at $3.50 a pound and we make $80,000 a year, that we will buy 5.29 pounds of beef a week. Okay. So let's see what else we can read off this table. It's the same table as before. So let's say we want to find f of 4, 20. Part B, find h when p equals 450 and c equals 484. C, find all values for household consumption when p is fixed at $3. So for part A, find f of 4, 20. Remember, our function was f of price, household income. So the price is $4 a pound, household income $20,000. So we want to go to the $4 column and see where that intersects with the $20,000 row. Okay, so $4, 20,000 row, they intersect at 2.51 pounds of consumption of beef. For part B, find h when p equals 450 and c equals 484. Price being 450 represents this column right here. And then the consumption is 4.84 pounds. So we go to this row, we find the 4.84 pounds, and then we look for the corresponding H, which would be 60,000. For part C, find all values for household consumption when P is fixed at $3 a pound. So when P is fixed at $3 a pound, our consumption, okay, is going to vary from 2.65 to 5.79. So the values would be 2.65, 4.14, 5.11, 5.35, and 5.79. So those are all the values that we could get for consumption when P is fixed at $3, because when it's fixed, we have the entire first column. Okay, not all tables have scenarios surrounding them. Sometimes they're just direct values. So let's look at what we can get from some direct values here. So notice here that we have a table, which is a function of x and y. Our x values are 0, 1, 2, and 3. Our y values are 0, 20, 40, 60, 80. We want to use this table to find the following things. A. Find little x when capital F is 102 and y is 80. Remember, capital F is our dependent variable, our function up here, this dependent variable f, which is represented by these middle values. B is f an increasing or decreasing function of x. C is f an increasing or decreasing function of y. And D, if y remains constant at 40, what are the values of f at x equals 0, 1, and 3? So for part A, we want to find x when capital F, our dependent variable, is 102 and y equals 80. So y equals 80 represents this bottom row right here. So that's the values we're looking across. Capital F is 102. So we're looking for the value of 102 within this row. It's the very last entry. So that means that my x value has to be 3, because it's where 3 and 80 intersect. For part B, is f increasing or decreasing function of f? How do we figure out if it's an increasing or decreasing function of one variable? So when we want to know if it's an increasing or decreasing function of x, what we want to do is we want to fix a value of y and look at what happens as x increases. So let's pick y equals 40. We fix that, so we're just going to look at one row, and we're going to look at what happens to the values as x increases. So we go 90, 95, 102, 111. As x increases from 0 to 3, our capital F values also increase. We can check another row, we'll get the same answer. If we fix y at 80, and we look at the values now of f as x increases, we go 81, 86, 93, 102. So we can see that as x increases, the capital F values also increase. So we say that f is an increasing function of x. Now for part C, we want to know if it's an increasing or decreasing function of y. So what we want to do is we want to fix one column, pick one x value, and then see what happens to the f values as the y values increase. So if we pick x equals 2, we fix that column, so we'll just look at this one column. We want to see what the f values are doing as y increases. So as y increases, we have 114, 108, 102, 97, 93. These values are decreasing. And you can check another column and you'll see that all the columns are decreasing. So f is a decreasing function of y. Part D. If y remains constant at 40, so now we have the row at 40 here, what are the values of f at x equals 0, 1, and 3? Well, if we're looking in the row of 40, when x equals 0, f is going to equal 90. When x equals 1, f is going to be 95, and when x equals 3, f will be 111. So these are just some of the things we can get off of a table of two variables. Let's look at some algebraic interpretation. Sometimes when we have a table, we want to figure out what the equation was that generated that table. So how do we do that? Well, here we have a table that represents revenue. Revenue is going to be a function of price and quantity. So here, the table reads across the top we have various prices, 100, 200, 300, 400, and various quantities, 200, 400, 600, 800, 1000, down the first column. If we look across the rows, we see there is a $100 increase for each one. So we want to look at the relationship between the increase in price and what's going on with our complete revenue function. So here, we want to look at the relationship first between price and revenue, and then we'll look at the relationship between quantity and revenue, and then we'll be able to put together our equation. So for price, the relationship for price, we're going to look at the change in revenue, however much we increase or decrease, divided by the change in price to give us what we're changing by from step to step. So here, to go from 75,000 to 110,000, we get 35,000. Okay, that's our change in revenue, divided by 100 to 200, that's 100. So change in revenue over change in price. Notice that's the same for all of these. So if you go from 110 to 145,000, again we're increasing 35,000, 200 to 300, increasing by 100. It's the same from step to step. So 35,000 divided by 100 gives us that the price factor that we're increasing is 350. We can do the same thing for quantity. We want to look at how much the quantity is changing and how much the revenue is changing and look at that relationship. So we're going to do again the change in revenue over change in quantity. So to go from 75,000 to 115,000, that's going to be a change of 40,000 divided by 200 to 400 is 200. And we can do this between any 2 points in this row, or in this column, excuse me. So again, if we check it at the bottom, 195,000 to 235,000, that's a change of 40,000, again divided by 800 to 1,000, which is 200. So that gives us a factor for our quantity changing of 200. Now this particular table is nice because it's linear for both variables. Not all tables are this way, but if you're asked to construct an equation, they will be. So here, we can now set up our general revenue function because we know the factors by which each are changing. So our total revenue is going to equal 350, that's our price factor in relationship to revenue, times P, plus 200, which was our quantity factor, times Q. So now we can get any of the values in the middle by plugging in the correct P and Q. So for example, if you were to plug in 800 for Q and 300 for P, you'll get 265,000, which is given on the table, and now we can also get it through an equation. Okay, so we've taken the time to read tables. We also want to go in the other direction where we start with a word problem, get a general setup, and also be able to set up a table on our own. So let's say a phone company charges $40 per month for a nationwide coverage plan and 10 cents per text message that is sent. Part A. We want to write a formula for the total cost, capital C, using the phone company service as a function of the number of months used and the number of text messages sent. So the total cost will be 40 times M, okay, so $40 per month, so we can plug in the number of months, plus 0.10 times T. Remember, when you're talking about change instead of dollars, you want to use a decimal point. So it's 10 cents per text message, T for text messages. Part B. Interpret C equals F of MT equals F of 3, 1200. So we want to calculate this both numerically and verbally to talk about what it represents. So first we can do a direct calculation by plugging in our numbers. What's going to be important here is order. Notice that our function is defined by months, comma, text messages, M, comma, T. That means the 3 gets plugged in for M and the 1200 gets plugged in for T. So that means if we take our original equation that we set up in part A, we're going to plug in a 3 for M, so we have 40 times 3, plus 0.10 times 1200. It's important that you plug the numbers into the correct variable. Crunching these numbers, we get that the total cost is $240. Now what does that mean? That means if we use 3 months of service, because 3 went with M, and we send 1,200 text messages, because 1,200 goes with T, it'll cost us $240. The big thing here is remembering which number goes with which variable and plugging them into the correct place. Okay, so now let's say we have another function. We have the function f is a function of x and y, which is 10x plus 2y. We want to create a table from this equation representing f of 0, 4, f of 1, 4, f of 2, 4, f of 0, 5, f of 1, 5, f of 2, 5. So the first entry in our function is going to be represented by x, because it says here it's going to be x comma y. So our x values are 0, 1, 2, 0, 1, 2. So when we choose to pick a side for x, we'll do that across the top, we need the values of 0, 1, and 2. Similarly, when we look at the y values, which are the second entry, we have 4, 4, 4, 5, 5, 5. So we need to represent 4 and 5 in our table. So we give those each their own space in this first column. Now to calculate the numbers in the middle, we just have to plug these into our equation. So for example, f of 0, 4 means we're plugging in a 0 for x and a 4 for y into our original equation. So we have 10 times 0 plus 2 times 4, which equals 8. So that means f of 0, 4, when x is 0 and y is 4, the capital F value is 8. So that's where we put it in our table. When x is 0 and y is 5, we should get a value of 10. Let's double check that. Okay, so we plug in a 0 for x and a 5 for y. 10 times 0 plus 2 times 5 is 10. So we put that in our table where 5 and 0 intersect according to our function. We can fill in the rest of the table accordingly. Let's do one more. Let's do f of 2 comma 5, this last value here. So we know that's where x is 2 and y is 5. So f of 2 comma 5. So we plug that into the original equation. So we have 10 times 2 plus 2 times 5, which equals 30. So that's what we fill in here. That's how we're going to generate our tables if we have the function to start with. Now we also want to talk about increasing and decreasing. So we want to know, is f an increasing or decreasing function of x, and is f an increasing or decreasing function of y? So let's start with x. So what we want to do is we want to fix a y value. So let's pick 4 and look at what happens to the f values as x increases. So as x increases, our values go from 8, 18, 28. So that means we are increasing. Notice that if we had picked y equals 5, our values still are increasing, 10, 20, 30. So we have an increasing function of x. Similarly, if we want to find out if it's an increasing or decreasing function of y, we fix an x value. So let's pick 1 and look at just this column and see what happens as the y values increase. So from 4 to 5, our f values go from 18 to 20. That's increasing. Notice if we picked the last column, we would go 28, 30, increasing, or 8, 10, increasing. So f is an increasing function of y. By now, we can understand how two variables can play an important role in changing the course of a function. But what if we wanted to investigate the effects of manipulating only one variable at a time? This is a really good thing to do with two variables to get an idea of what's going on overall. So we can do this by holding one variable fixed while using different values for the other variable to see how it affects our function. This gives us a function with only one variable, and this is known as a cross-section of the original function. So let's see how this works. We'll do a lot more of this in 9.2 and 9.3, but let's get started. So suppose a drug is administered to a patient at Cooley Dickinson Hospital to help reduce the patient's pain level after a hard fall. The concentration of the drug, capital C, is a function of the amount of drug administered, D, and the time since it was administered, T. and can be modeled by C equals f of d comma t equals te raised to the negative t times 5 minus d, where d, which is the amount of drug, is going to be between 0 and 4 milligrams, and time will be positive. We want to write a function representing a cross-section that fixes the value of d at 4. What does this trend of the cross-section tell us about the effects of the dose over time? So here we have an original function that has two variables, and we're going to fix the dose at 4 milligrams. So if we plug in a 4 for d here, which you can see, we get the function f of 4 comma t, which equals c, which equals te to the negative t times 1. Okay, this is going to be a surge function, and what we see is that the concentration over time will increase. It'll peak at 1, which is what we expect, because surge functions have a maximum at 1 over b, and our b here is 1. And then over time, it'll slowly dissipate out of the body. So here, this graph represents what's going to happen to the concentration over time when d equals 4 specifically. Now, if we change d, it would affect things like where our maximum happened and how quickly things came out of the body. But here, by fixing one value, we see that we now have a function of one variable, and it's easier to talk about what's happening. So what if we fix the other variable? What if we pick a specific time? So let's write a function representing a cross-section that fixes the value at t equals 1. So time equals 1. What does the trend of this cross-section tell us about the concentration? So when time equals 1, so after 1 hour, we have f of d comma 1, and our concentration is 1e to the negative 1, 5 minus d. So if you graph this, you can graph this on your calculator, or the graph is provided here, we see that depending on the dose, as the dose goes up, the concentration in the bloodstream goes up. So that means that if we had given you a dose of 1 milligram, that after 1 hour the concentration would be less than 0.1, and if we had given you a dose of 4 milligrams, that after 1 hour the concentration would be 0.4. This should make sense because a higher dose means that if we check everything at the same time, that the person who got the higher dose has a higher concentration in their blood. But you can see again that by fixing one variable, we're reduced to a one variable problem, so it's easier to interpret what's going on.